Hi, our next lesson is essential review, but really a deeper dive into polynomial arithmetic. And remember, when we say arithmetic, what we mean is performing operations on polynomials. So really the main prior knowledge we really need today is basic operations on polynomials, and we'll really need our thinking caps on a little bit today. For our warm-up, we're just going to start with some basic operations. So I'd like you to find the sum, difference, and product of these two polynomials I've given here, okay? And don't forget, when we say sum, we mean to add them. Difference is subtract, and product means to multiply. So I'd like you to please pause right now, then we'll come together and we'll do those together to check your work. Let's go ahead and check our answers for this now. I do realize that, especially for the sum and difference, it's likely that you were able to just look at these and know how to combine the like terms to get the proper answer, and that's totally okay. I do like showing you this way because it really helps us remember that these are just like place value, like our ones and tens and hundreds and thousands. Every exponent that is identical is a like term because it lines up in the same place value. Okay, so that's why I like to do it this way. But anyway, let's go ahead and get to the answers. Technically speaking, we're kind of missing the x squareds in this, so if I want, I could think of 0x squared, and same for the x to the fourths in this one, and I can do the same over here. And anyway, we'll just go ahead and finish it off. 4x to the fourth plus 0x to the fourth, I still have 4x to the fourth. Negative 11 plus 8 gives me minus 3x cubed. 0 plus 5 gives me 5x squared, it stays as 5. 9 plus negative 3 gives me plus 6x, and 2 plus 7 is 9. So there's our sum, our difference. Now we're subtracting all of those, and it's easy to accidentally get mixed up with this if maybe you subtract some of them and you forget and you add later. This is why I put the subtraction with the parentheses there, is really important. So that leaves 4x to the fourth again. Negative 11 minus 8 this time actually is negative 19x cubed. 0 minus 5 gives me minus 5x squared. 9 minus negative 3, that's a tricky one, but that turns into adding, so it's going to be 9 plus 3, which is 12. And then 2 minus 7 gives me negative 5. So there is my polynomial that is the difference of the two. Now we'll get to one we've been doing a lot for a long time, but really helpful. Now I've noticed recently some people have been making mistakes when you don't use the expansion box especially for these long ones. And again, I'm going to encourage you, it's really helpful for you to get used to using the expansion box. Again, it organizes all the things for you really quickly. So let's go ahead and look at this. If we're filling this out, this is going to be 8 times 4, which is 32x to the 7th, right? And I'm just going to color code this because it sounds like fun to me. The way I've color-coded this, all the ones that are the same color as each other, they're all on these diagonals here, and those are the like terms. So it helps me keep it all organized, and I can put it into the final answer. So my final answer here is going to be the sum of all those pieces, right? Each with each. Okay? I've multiplied each term there with each term there, and I'm going to add them all together. So I'm going to get 32x to the 7th. Negative 88 plus 20 is negative 68x to the 6th. Negative 0 minus 55 minus 12 is negative 67x to the 5th. I might run out of room. 72 plus 33 is 105 plus 28 is 125, 133. x to the fourth. 16 plus 45 is 50, 61. Minus 77 is minus 16x cubed. I'm going to have to go on to two lines here. And then I have 10 minus 27 is minus 17x squared. Negative 6 plus 63 is plus 57x plus 14. Whew, that took some work. Example is sort of another warm-up, I guess, but it is a review question, but it's a great application of some of the problems we're going to look at today. We're going to revisit something we've answered before. So I would suggest that you go look back in your notes from the first section in this investigation that we did, and the one where we were talking about rolling dice, and we made a table for all the totals and the dice, and we actually realized that there's a polynomial that can help us answer this. Now that you've found your notes and looked back at that example before, I've already written out how we would solve this to remind you, because it's probably a little tricky, so we'll just do it all together. So if you remember, if I have a 5-sided dice, and our other one it was a regular die, which is 6 sides, right? And so we went x to the 1 plus x squared all the way up to x to the 6th before, but now we're going to stop at x to the 5th because we're talking 5-sided dice. Okay? And just to recall for you guys, we set up a table before for 1 through 5 and 1 through 5 so we could look at all the different possibilities for the total I could get when I rolled 2 dice, right? Well, we did 1 through 6. And then we realized that if I actually made the multiplication, the expansion box for this polynomial, the exponents on there actually are the same numbers as the totals. And it actually is really cool that polynomial multiplication can be used to answer a question like this. So let's go through this again together. Because I have two die, then I can take this polynomial and square it, and all the different exponents you get in your final result represent the different totals that are possible. But all we're looking for is rolling a total of 9. So if I have my x to the 9th term is going to be somewhere when I multiply all this out. Now just to remind you guys, the very highest term I'm going to be able to get is x to the 5th times x to the 5th, which is going to give me x to the 10th. And if you think about 2 5-sided dice, there's only one way to roll a 10 total, because the highest number on both die is 5. So there's only one way, a 5 and a 5, right? But when you get your in-between numbers, you can actually get multiple ways to find it. So here's what we're going to do. We're going to practice some mental math here. It's actually, the big point we're making in today's lesson is it's very helpful to be able to actually do some things in our head and think ahead of time. And that's why this example is really helpful, and since we've already looked at it, then that's why we're starting with this example. Now let's think. How can we make an x to the 9th if I'm multiplying this all out? I'm not going to want to multiply the whole thing with an expansion box or anything. I'm going to try to do this in my head without doing the work, okay? So let's think. X to the 1 is going to be multiplied by all these. Once it multiplies, are any of these going to get up to x to the 9th? No, because x to the 1, the highest one over here is x to the 5th. When you multiply those, it's going to make x to the 6th. X squared, well, again, let's match it with the highest one here. When I multiply that with x to the 5th, it's still not going to be x to the 9th yet. And this is going to not work either, because the highest thing here with the x to the 3rd is going to make x to the 8th. But we do get an x to the 9th finally. So if I look at this x to the 4th and this x to the 5th, if I were to multiply the whole thing out, this times this is going to give me an x to the 9th. And then there's another pair of like terms that we'll look at here as well. Because it looks like this x to the 5th with that x to the 4th is going to make another x to the 9th. And I'm pretty sure none of the other powers of x in either of these polynomials is going to end up being multiplied by anything in the other one that's going to get x to the 9th. So it looks like I have one there, pair, and then another pair there. And so in the end here, my full polynomial, if I were multiplying this all out, is going to end up having 2x to the 9th. So guess what? My answer for this is, how many ways are there to roll a total of 9 with 2 5-sided dice? We use this polynomial multiplication, and this coefficient is my answer. There are two ways. So now let's just dive into some more of these mental math prediction problems. Our next example, example 2. Find the coefficient on x to the 5th in the normal form of the following polynomials. So it's really the same type of question as we answered a moment ago, but with that dice problem, it's really cool. Again, it's really cool to realize that polynomials actually can help model a lot of things, and you can answer some questions with something that just seems like that it's unrelated to anything. So it turns out polynomials are really actually related to so many things in the real world. But anyway, we're just going to dive into just some pure mathematical examples for now to get practice with this. So each of these, none of these is in normal form. So when I say in the normal form, what I mean is if we were to actually simplify these or expand them and put them into normal form completely, but we don't want to actually do that. Normally we ask you, make sure you show all your work and stuff. But since our focus on this lesson is actually doing this mentally, then let's try not to just show everything out and just try to figure out ways to do it. So I want you to try to tackle these on your own, at least A and B, and then we'll look at C together. And then let's check our answers together. So please pause now and do A and B and work those through yourself, and then we'll look at them. Okay, so now that you have actually looked at these and worked on them, and you have an answer, right? Let's go ahead and take a look. I'm going to use another color just to maybe underline the pieces that are going to matter to my final thing. I want to know the coefficient on x to the 5th. Well, since this one's just all combining like terms, be careful because you notice it's not in normal form, because normal form we need the highest exponent all the way down. But also, here's the thing, since this is all added and subtracted, this exponent's not going to change at all for any of these terms. The only thing that's going to happen is combining like terms. So what we have here is 8x to the 5th minus 2x to the 5th, which is going to give me a 6x to the 5th. So my actual answer here is, the coefficient is 6. Because once this was all written out and simplified, you see that we have 6x to the 5th. Okay? Now, this one was just simply combining like terms, adding, subtracting. The next one is multiplication. So again, I'm assuming that you've worked this through on your own. Let's go ahead and see, kind of like we talked about last time, what are some combinations of things that are going to combine to make x to the 5th? I see 8x to the 4th, and is there anything, once I multiply this with all those things, are any of them going to end up 5th? I think so. I think those two are going to match to make 5ths, right? And we may do a little bit of writing on here, but that's okay. We don't have to do all the multiplying. And then I think I see that this x to the 3rd, once I multiply it with that x squared, is going to make it x to the 5th. And then this negative 1 over here, no, it's not going to make x to the 5th with anything. And this and this, neither of those two terms are going to end up multiplying with anything there either. So guess what we have? In the end, we're going to have a bunch of stuff, but we're going to have 8x to the 4th times 7x, and that's going to actually make 56x to the 5th. And then this 2x cubed times 2x squared is going to make a 4, positive 4, x to the 5th. And then there's going to be a bunch of other stuff in there once I do all the multiplying. But remember, all I'm trying to answer is, what's the coefficient on x to the 5th? So since we thought that through, there's going to be 56 plus 4. And I guess my final answer, I've normally been writing these in orange actually, so let's keep that in orange. My final answer, 56 plus 4, is the total is going to be 60x to the 5th. But 60 is my answer because we're wondering what the coefficient will be. So we predicted that it's going to be 60, and we didn't have to do all the multiplying to figure that out. Now, maybe you've looked at C already, or hopefully you have, but I'm just hoping that you realize that this right here we've already answered because that was part B, and this one right here we've also already answered because that was from part A. And the good thing is, these are just being added, so they're not multiplied. That would get pretty complicated pretty quick, and we're not going to worry about that. But you'll notice here that we already know our answer from this. We got that this is going to be 60x to the fifth, and since this is all added, and of course there's other stuff involved, and this one ended up being 6x to the fifth, and again, the whole thing's going to have much more to it, but again, we only care about x to the fifths. So if I have 60 plus 6x to the fifth, what we're going to have is 66x to the fifth. So 66x to the fifth will be my total of the x to the fifth. So my actual answer is, what's the coefficient on x to the fifth? The coefficient there would be 66. So you see, we can actually predict a lot of these things, and in fact, if we get fluent enough, we may be able to do the whole multiplication in our head. But again, a lot of times we only care to answer one piece of it, okay? So let's move on to another example that's doing some more of this mental kind of work. Last couple examples here. Number 3, without expanding, explain why the following is not an identity. Okay, and let's remember again, we've been talking about this word a lot. What is an identity? It's an equation that's always true, right? So just to remember, this means it's an equation that's always true. All right, always true equation. Okay, this is super important of an idea. Now you can just think, identity, identical. That'll help you remember it. But anyway, why is this not an identity? Well, if you look carefully at this, again, this is kind of like mental math. Why is it that when this guy, if you actually do the product, is not the same as this? Well, we could probably see right off the bat one thing pretty quick. So I'll just be honest, it'd be easiest just to look at these first two terms. 2x cubed times 7x squared is equal to 14x to the fifth, not 14x to the sixth. So that right there, that first one makes it so it's, it's not, this one is not equal to that one always. There might be an x value you could find that makes them all equal. And in fact, I think I can see one right now. I think if you plugged in 0 for x here and here, it would actually make that equation true. But identity means it's just always true. And since this does not expand and simplify to be exactly equal to that, then it's not an identity. Okay, and the last one here I thought we'd look at is just finding some missing pieces again. We've looked at one similar to this in the past. If I actually have an equation here, and I want to say, when is this always equal to this? What k value should make it be true? Okay? And when I say true, again, I'm actually this means I want it to be an identity. Okay? Again, an identity just means it's always true or identical. So let's just take a look at these. This would be one where I actually think it'd be valuable for you to pause the video and work on it yourself, because we kind of know how to do all of these at this point. So why don't you go ahead and pause it right now, and then we'll do them together and then be done. Well, okay, this is just simply an addition problem. And you can see this has x squared, but this part doesn't. So it's still going to be 13x squared. But the real thing where this missing coefficient in this case is the x coefficient. Well, this has an x on it, doesn't it? So if we have kx plus 9x here, those need to be equal to 12x. So if you wanted to, you could say kx plus 9x is going to have to equal 12x, right? And at that point, you could probably just realize that k needs to be 3. If you really wanted to be thorough, you could say k plus 9 times x equals 12x, and therefore k plus 9 equals 12, and so k equals 3. You don't have to do all those steps, but this is just kind of the complete way of really showing it all out. But either way, yeah, k equals 3. This one is, instead, it's a product, but it's one of the simpler products. So again, this is one that we want to be in the habit of being able to kind of do these in our head. Again, where's the k value? And let's identify where that actually fits into other things here. Well, that k is the thing at the end, and there's different ways we could go about it. Hopefully you realize if we actually expand this out, we get x squared plus 4x plus kx plus 4k. So just just to help us out here, we already know that that's x squared, but this should be equal to 7x, shouldn't it? And this right here needs to equal 12. So I think we could actually figure out what k is from either of these. If I have 4x plus kx equals 7x, you can probably realize k has to be 3. You can also think 4 times k equals 12, so of course again k must be 3. So either way, we get the same actual k value as the other one here. K must be 3. And it just helps to remember that this number comes from adding the two 4 and k, and then this number here comes from multiplying those two. And last but not least, it's similar, except it's actually got this part is what is missing, right? Well, this one, I don't know, it might be a little easier, because really what you could do is you could just expand this out and you can figure out what k is. So x squared minus 3x plus 8x minus 24. So I think we can see that this there is going to give me 5x minus 24, so we can see k equals 5. Okay, so that should do it for this lesson, and we'll see you next time. Happy math. See you later.